Bismillahir Rahmanir Rahim. We had delivered earlier lectures in class up to lecture number 10. In first 9 lectures, we covered the first part of the course, that was to develop a frequency domain model for the dynamic system, for dynamic linear time invariant system that was represented by linear constant coefficients ordinary differential equations. Since we are starting now after lapse of certain weeks, so first of all I will go through the salient features of lecture number 10. That was the same topic, time response. Here is the summary of last time lectures. Chapter 4 of our textbooks, time response. We covered section 4.2 and 4.3 in lecture number 10. Today in lecture number 11, we will be covering section 4.4 and 4.5. And inshallah, the next lecture, lecture number 12, we will continue chapter 4. So what was the main topics, salient points of section 4.2? First thing is, a linear time invariant system is modeled by a transfer function that is obtained from the underlying linear constant coefficient ordinary differential equations, and these equations are transformed through Laplace transform to give us the transfer function, that is output over input. A transfer function in general is ratio of two polynomials. We have a numerator polynomial ns, a denominator polynomial ds. The roots of ns produce zeros of the transfer function. That means you have ns you put it equal to 0. You solve this equation, and what you get is the zeros of the transfer function. And zeros implies that the system will produce no output but an input of that complex frequency. For example, if we have a factor of, let's say, s minus 2, other s plus 2. This is a factor of ns. So this gives us a root at s equal to minus 2. Now if you apply an input at s equal to minus 2, then the gain of the system will go to 0. So that's what is called the zeros of the transfer function. Similarly, if you put ds equal to 0 and solve for the roots of ds, that will produce poles of the transfer function. The system has natural frequencies of oscillations. System response can be divided into two parts. We have natural response and we have forced response. The natural response is when the input is 0, and this is from system itself. The forced response, when you apply an external input with 0 initial conditions, system will have a response, and that is called the forced response, or the response due to a forcing function. Last time we discussed that the poles of the transfer function produce the form of the natural response, and the poles of the transfer input function generates the form of forced response. For example, if our input is Rs, a step function equal to 1 over S. Now here is a pole at 0, S equal to 0. So this function, this pole at S equal to 0 will generate the form of forced response. 0, the transfer function, have no effect on the time domain parameters, but it does alter the relative amplitude of the force and natural response. So what are the effect of zeros on the system response? That is the natural response and the forced response. Here is an example. We have a transfer function that is given by 1 over S plus 1. So it has a pole at S equal to minus A, where A is greater than 0, so the system is stable. The pole is the left half S plane on the real axis, single pole. So the time constant is defined as the time for exponential function to decay to 37% of initial value, because if we take the inverse Laplace of this will be equal to minus A t. Inverse Laplace of 1 over S plus A, that will be the time response. So this function is a decaying function. As the time goes to infinity, this will go to 0, but it will start at 1. So we defined time constant as, for example, this is a function, start from 0 and goes like this. So this is 1. So when the response is 0.37, let's say this is 0.37 of the initial value. So this time is called this time. This time is called the time constant of the system. So rise time is the time for waveform to go from 0.1 to 0.9 of the final value. For example, if you take a step response of the system, the step response goes like this. So 0.1, let's say this is 0.1. Here the final value is 1. So when the final value goes to 0.9, so this time from this to this time is called rise time of the system. Then we have settling time, the time of the response to reach and stay within 2% of its final value. That means, if for example this is the final value, when it comes between these 2 points, this is, let's say, if it is 1, this is 1.1, this is 0.9. The response comes within this envelope, then this is the settling time, where it starts to get into this envelope. Important note is that all these 3 parameters for the first order system, the time constant, the rise time, the settling time, they are inversely proportional to the pole location. This is pole, this is pole, this is pole. So they are all 3 are inversely proportional to the time constant, to the pole location. So if pole is close to imaginary axis, let's say it is 0, so all of them go to infinity. And if pole is at minus infinity, then all of them go to 0. So we can see here that the pole location is important. A system which decays very fast has to have pole away from imaginary axis. Then we discussed about the salient points of section 4.3 was how does a zero affect the response of first order system. We take a simple example. C1s is our transfer function, that is, this is output C1 of s is equal to a over s plus a. So you multiply this by a 0 which is at minus z, so we multiply this one by s plus z. So this is the output, so we have a step input which is s. So a over s into s plus a is our C1 of s, and we add a 0 here which is s plus z at s is equal to minus z. So we get C2s is a s plus z over s plus s into s plus a. Its derivative as C2s is equal to this function. Now by using the initial and the final value theorem of the Laplace transform, we get C2 infinity is equal to z, and C2 0 is a, and the derivative at 0 is infinity. So by adding a 0, we have three different results as compared to without a 0. So these are the effects of the 0 on the first order system. First is, we amplify the steady response by z. It should have been 1 here if there was no 0. Now it is z. So if z is 2, the response will settle down to 2. If it is 3, the response will settle down to 3. Second point is, we raise the initial value from 0 to a. So now initial value is not 0, and the response is not starting at like this at 0, but it is starting at a. So we have something like, we go to, this is a, and the response will come down from here. This is the effect of 0. And the third thing is, which I already shown, is it has infinite slope. You can see here the slope is infinite here. It immediately goes to a value a. But it's not practical because we have made some mistakes or some simplification in our model. For example, for a DC motor, we had first order model, and that was the result of neglecting the inductance of the armatures. So that incomplete model or simple model resulted in first order system. That is not physical. It's not physical because DC motor cannot immediately go to a very high speed and then come down to its steady state speed. Today we start with section 4.4. This is second order system. Now first order system is not very attractive because it has limited time domain specifications. We saw it, there were only 3 of them. But second order system are more attractive, especially when they have a certain range of the damping ratio. So first order system only give us speed of the response, that is the pole of the system will change only the speed of the response, and speed, this is everything is inversely proportional to the pole location. But the second order system has 2 parameters. So by virtue of these two poles and changes in the parameters resulting from the movement of two poles in S-plane, we can have changes in the form of the response, the form, not only the speed but the form of the response. How do we get the second order system model? A simple example, this is an electrical system. Here we have an inductor, resistor and capacitor in series, and we can model them by saying that this is our Laplace transform of, this is SL, this is R, and this is 1 over SC. Then we apply simple Kirchhoff voltage law and we end up with this model. The thing to note is that we have a 1 here. It is important because we use this information later on also. We have to have 1. That means S square should have a coefficient of 1. This is a mechanical system, mass, spring and damper system, and here again we end up with a second order model. Here it is M, so you have to divide throughout M, so you will get F here as M. This will become K over M. This will become 1 over M. This M will go out. So we'll have S square plus FV over M S plus K over M, and in the numerator we will have 1 over M. So here is a second order transfer function, a general transfer function. That means it is applicable to all second order systems, electrical, mechanical or others. They will have the transfer function of the form Gs equal to omega n square over S square plus 2 zeta omega ns plus omega n square. Again, this coefficient is 1. So omega n square will be equal to, from electrical network, it will be 1 over square root LC, and then we have 2 zeta omega n will be equal to R over L. Mass spring damper system, omega n is square root K over M, and 2 zeta omega n is F of V over M. So what we did, we just compared the coefficients. You compare the coefficients. So in section 4.5, now we look at the poles, how they move in the S-plane as we change the parameters omega n and zeta, which are derived from the pole's location. They depend on the pole's location, omega n and zeta. Omega n is called the natural frequency, or the undamped natural frequency of oscillation. For example, the frequency of oscillation of a series RLC circuit with resistance shorted. If you short R equal to 0, then what you get is omega n is equal to 1 over LC square root. Damping ratio qualitatively is defined as exponential decay frequency, natural frequency of oscillation. That means it will have two components, ratio 2 components. This is the decay frequency, and then we have, within this we have oscillations. So they have frequency which is here, and this frequency is given here. So further you can simplify this into time. So 1 over 2 pi natural period over exponential time constant. So we can relate this to time also. So now we want to find the poles of the system in terms of the two parameter zeta and omega n. So how do you find? We just say ds is equal to 0. We solve for the roots of the equation, and the two poles are minus zeta omega n plus minus omega n zeta square minus 1. Now zeta is a damping, so we don't talk about negative values. We only have our required ranges, which is zeta is greater than 0. That is the range of interest. Zeta greater than 1. Then we have other milestones here. One is zeta equal to 0, between 0 and 1, equal to 1, and greater than 1. We'll see why we are dividing this into these 4 segments. So here the summary. When zeta is 0, if you put zeta 0 in that equation, which is this equation, so we end up when zeta is 0, this term goes to 0, this term is minus 1, so we get minus 1 square root will be j, which is plus minus j omega n. When zeta is between 1 and 0, we can switch this one, we can make it take minus 1 common, so we have 1 minus zeta square, like this, 1 minus zeta square, and we have put a j here now. So these are our roots, and this is the most interesting case, which is the under damped case. This is the form of the response. Remember, this is not only the speed but form, as we mentioned. So with change in zeta, the response form also changes. Undamped, underdamped. Zeta is equal to 1, it is called critically damped because this term goes to 0. This is once it is simply minus omega n. We have repeated poles at omega n, 2 poles at omega n. And zeta is greater than 1, so we have 2 poles now. They are real, but they are different, unequal real poles. So one pole moves to infinity as zeta increases, other poles goes to 0 as the value of zeta increases. So here are the responses. So when zeta is 0, we have imaginary poles, pair of imaginary poles. One is here, one is here, and this is the response, is basically oscillatory response. It is undamped. There is no decaying term here that will reduce this oscillation to 0. It will keep on it will continue up to infinity. When zeta is between 0 and 1, so we are here. So if the poles will move like this, this pole moves like this, and this pole moves like this. And this is the value of zeta between 0 and 1. The pole is moving. We have shown a pole here and a pole here now. When zeta is exactly equal to 1, so we have 2 repeated real poles. We have come to this point. This has come here, this pole has moved here. This is a point. We have 2 poles now here. Now as zeta gets larger, so we start from here. One pole moves this way and the second pole moves this way. And here is the response, is this one. So these 3 responses are not very interesting. This one, this one, this one. This is the most interesting response because it will cover majority of the time domain parameters. And our next section we are going to discuss this response, which is underdamped response. Is a special, we draw special attention toward this response because this will give us the majority of the time domain parameters. This is it all together, plotted all together. So step response of second order system for various damping ratios. So you can see here, this is, we start from zeta equal to 0. We increase zeta to 0.2, then to 0.5, and then ultimately we have zeta equal to 1. So as zeta is increased from 0 to 1, the oscillation stop because the poles are going from imaginary to complex, then to real poles. So at critically damped case, we have 2 poles, they are equal and they are real. Further increase in zeta will come here and this is the overdamped case. Here the poles are not equal, they are unequal pole, but they are real now. So when the poles are real, there is no oscillation. When poles are either complex conjugate or imaginary, then we have the frequencies, then we have some oscillations. So this takes care of our slides, and then in the next lecture, so before we finish, we have got a simple example. This example is from your book, which is 4.3, example 4.3. We are given a system, a second order system transfer function, and remember this is also 1 here. If there is no 1 here, you have to divide this before you can compare with our standard form, s square plus 2 zeta omega ns plus omega n square. Now what we do is to find the value of parameters zeta and omega n. So we can see the 36 means this is the same as omega n square, and we have omega n square is equal to 36, therefore omega n is equal to 6 radian per second. To find the value of zeta, we take the second term, which is 4.2, and this coefficient is equal to 2 zeta omega n. So 2 zeta omega n is equal to 4.2. We have found zeta before, which is 6. So from there, then we can find zeta is equal, we have found omega n equal to 6 radian per second. We can find omega n as 4.2 over 6 into 2, which gives us zeta equal to 0.35. This value lies between 0 and 1. So this response, system response, is underdamped. It's underdamped response. Inshallah, next time we will continue this lecture, lecture 12. We will move on to the other sections of the same chapter. Thank you very much.